so our first speaker for this session is Omri Ben-Eliezer. He'll be speaking about to work with Microsoft. Thank you, Samson. Some important sheet of who's here.
I'm moving.
And Sandeep who is here. And with the pleasure of having all the co-authors being here. In this topic, basically, I want to reconsider the standard model of robustness. But let's maybe revisit the standard model. So, as Samson presented, so basically we have some underlying universe of possible elements. The size of the universe is n, and the stream is basically just so it is a collection of updates that arrive one by one. Each update is a combination of an element from the universe, and whether we insert the element or delete the element. The plus minus one, whether we insert a single element or delete a single element, is an assumption we make just for convenience. The results we hold for general insertions and deletions, we sum them. In general, the algorithm is required at any given time to output a good approximation of a 1 plus epsilon approximation of some function f on the frequency vector. So, for example, the frequency moment, f2, for example, this is going to be a random example. And in general, the underlying assumption is that the adversary is adaptive and it is quite powerful. It can memorize the entire history of an interaction. So the update number I of the adversary can depend on all previous stream updates, everything that the adversary generated so far. This is not unique to the robust setting. It's also true in the oblivious world, but it also depends on all the outputs of the algorithm so far. All right, and one, I think, fundamental open problem in this field, which Samson also mentioned to some extent, is the problem of getting efficient streaming algorithms for moment estimation in general. Let's say F2, for example, in the case that we have both insertions and deletions in the stream. So we both are able to insert a single unit of some element or delete. So you mentioned in the insertion-only world, things are much more efficient. Algorithms are polylogarithmic in all the heavy parameters, in the length of the stream, in the size of the universe, and so on. But when we have both insertions and deletions, we don't yet know what to do very efficiently. So in contrast to the oblivious world, where the AMS sketch gives basically logarithmic in a space algorithm, in the robust world, we were not quite yet there. So the basic frameworks of step switching and computation tests don't give anything meaningful in this regime. Space and algorithm is trivial. The differential privacy framework was the first to go below this linear bound. Gets square root of the length of the stream. And this is unfortunately tight in general. It's not necessarily, I mean, the use of differential privacy framework is not specific, it doesn't have to be specifically tight for moment estimation, but for general streaming problems, this framework is cut there. And then there came a couple of frameworks that got below this square root of n barrier. So the first of them was with Talia and Shishabana, and it got n to the 0.4 roughly. So it basically interlaces between dense regime and sparse regime. And the dense regime, we use the differential privacy framework, and the sparse regime, we use sparse recovery. This gets to n to the 0.4, and there's a more recent work by David Woodruff and Samson It gets, well, for F2, it gets the same bound up to lower order terms, but it gets some improvement for F3 for other values of P. And it will make another visit to our talk later on. This, okay, so but the bottom line is in the oblivious world where we don't have any robust any adaptivity, we have algorithms that are algorithmic in the amount of space it is, logarithmic in the length of the stream, and in the robust setting, that we know is n to the 0.4, it's exponentially worse, and getting either to close this to close this exponential gap or explain why it's such a gap mass. This is, I think, it's one of the most important problems in robust streaming. Well, in this talk, we're not going to solve this problem, but we are going to try to bypass this this kind of forced case, I think. If you revisit this standard adversarial model, you may notice that, well, a streaming algorithm is usually required to have very limited space that maybe is maybe logarithmic or some small polynomial in the length of the stream, whereas the adversary can memorize the entire history, so the space is as big as linear. At least in terms of memory consumption, space consumption, it is much more powerful than the algorithm. And this is maybe kind of strange. No, I mean we assume quite a lot of the adversary, and maybe it shouldn't always be the case. I mean, there are some settings where it does make sense to assume that the adversary is very strong and very evil. I don't know, but it's not always the case that the stream is must be generated because some of it is so evil and so powerful. Okay, so the main question that I would like to consider is to design efficient adversarial robust algorithms for, let's say, turnstile F2, I mean insertion and deletion F2, when the adversary is roughly as powerful as the algorithm. In fact, the results that we will have are for the setting where the adversary is even weaker. Yeah. All right. Maybe one also real world motivation for studying these kind of adversaries that are maybe as powerful as the steering algorithm, maybe bounded space. So this is Herb Simon, the very famous economist and one of the founders of the CMU CS department. And curiously enough, he won both the Turing Award and the Nobel Prize. And wanted to ask whether anyone knows how many people there are that won both prizes.
At least one more.
At least one.
It's not the approximation.
God got you that.
No.
You mean like 2 Nobel Prize or also?
Well, as of I think 2023, the number was 1. That.
Oh,
But Josh didn't on both of them, I think, in recent years. So
what
that
was Nobel Prize? What was Nobel Prize for?
I know that
Was it for?
in physics, I know some other people. So the DeepMind founder, but in physics, I don't remember. So who got that?
Yeah.
Also physics. Okay, good. Yeah. Yeah, and he proposed the interesting model concept of bounded rationality in economics. So basically, people don't make decisions based on this. In most cases, they don't make decisions based on a huge amount of information. They are rather like computationally constrained entities. And when we think of the adversarial robust setting, I think one of the strongest motivation, it's not the only motivation, but one of the strongest motivations for studying this model is as to understand what happens when there is a cycle for the field. So basically, the algorithm, so the street, the person, let's say in this case, wants something that they want to watch some TV show on Netflix, and then the algorithm provides this provides the next set of possible TV shows to the person. It's a set, it's not a single show, and then the person picks from this set of possible shows, picks another one. So and it sends it to Netflix, and then Netflix provides another set of options, and so on. So this is a setting that is not adversarial. I mean, I want to watch good TV shows. I want to enjoy them. I don't want to fight with the Netflix algorithm. But I'm certainly adaptive. I mean, the decisions I make are definitely depend on what Netflix offers me. But on the other hand, I'm also bounded rationality. I'm not very smart. And again, I'm not certainly not adversarial. So I think this is kind of a fundamental setting where we want robustness. We want algorithms that are good against adaptive entities that are not explicitly adversarial. Okay. So the big question that we want to answer, we're not going to answer it yet, but I want to mention it here. In general, this is a topic with many open questions. I think the number of questions is like linear the number of slides. The constant is less than one, but there's quite a bit of quite a number of open questions. So the motivating question is to design an algorithm, an adversarial robust algorithm for, let's say, F2 estimation, turnstile settings such as deletions, against adversaries that are also space bounded. So they have some amount of memory, and we want the algorithm to be polylogarithmic in the usual big quantities, which are the length to a string m and the size of the universe n, and also just polynomial in the space of the adversary. So I'm not going to solve this motivating question. I think this is a very interesting question, and one that may be easier than solving turnstile F2 in the worst case setting. What we are going to look into a little bit. I would like to remark that there are a number of interesting beyond worst case of other beyond worst case models in robust framing. And the most notable example is a work by Ulrich with Moshe Shechner and Meni Sodiguchi. So they consider a couple of models. One is a model with advice. The other one is a bounded interaction model. There's also additional work on the bounded interaction model, including by some people that sit here. All right. So without further ado, I want to specify this low memory adversary. It may look a little bit complicated, but we'll go over it component by component and then try to convince you that these components make sense, and this is not overly specified. It is like the right one, perhaps. All right. So we still have full adaptivity. So the adversary at any round sends an update, and the algorithm sends an estimate, which is again the 1 plus epsilon approximation of the value of the function, the F2 value, for example, so far. All right, but how do we produce these updates? So the adversary has several types of memory. One type of memory is the estimate memory, and this estimate memory, it only keeps the last output, or you could call it also the algorithm output memory. It only keeps the last output of the algorithm, and it's a read-only memory. So basically, the adversary in some ways makes decisions only based on the last output of the algorithm. So this is the estimate memory. And another memory that that it has. It's a read-write memory, and this is the working memory. In the beginning of each round, this memory is erased, so it starts empty every round. You cannot keep information from previous rounds of the process. But this memory is unlimited. So at any given round, we think of the adversary as being able to make a complicated computation based on the information that it has. It's fine. In some cases, we also allow the adversary to keep a tiny amount of what we call a persistent memory. This is memory that is carried on from previous rounds. So if in cases where we don't have, in some cases, maybe arguably the most interesting case, the most interesting results that we have are in the case that you don't have this persistent memory at all. And in this case, we call it a memoryless adversary. And so this is the third type of memory. This is the, in some way, the only type of memory that is carried. So basically, in the worst case adversarial setting, this persistent memory is very large. It can be as large as M. We want it to be very small. Say that it will have size B bits, and B is very, very small. And the last type of data that we have is we have read access to some to randomness. We're also allowed to generate fresh randomness in an oblivious way. So this randomness tape is completely oblivious. It doesn't change as the algorithm continues. We are able to generate more and more fresh randomness that is again oblivious if we want. Questions about this one? Yes.
Is the adversary allowed to go back and look at both randomness?
No,
Shouldn't be a problem.
so it shouldn't be.
Yeah, all right.
I'm hesitant to commit, but if Kirsten is willing, then
It's gonna be my problem.
Because it almost feels like more memory if you're allowed to look at all random.
yeah.
But you're
so-
saying maybe the results are the same.
I mean, this type is fixed. We can think of it as fixed. So you can generate oblivious randomness as much as you want, and I think all of the results will hold if you assume that you memorize this. Yeah, if you want to think about humans, so humans are we have very elaborate long-term memory, and you can think of this as oblivious randomness. But when we make short-term decisions, our working memory, our short-term memory is very, very insufficient. It's very, very small. So if the debate is between 4 and 7 items. So this maybe the persistent memory is tiny. It's between 4 and 7 words. I mean, this is the most important side. So it's, I'm taking questions. It's fine.
And you also mentioned the working memory is allowed to be very big. Do you know if you get anything stronger? Do you also bound that by B?
No, I think we don't have. Yeah, I can't. I don't have anything small to say about.
So what is the setup for the randomness? That it's you cannot go back and read over randomness or not?
I think we can. Okay. Yeah. So yeah. Yeah. So we can generate a bunch of randomness in the beginning and read it. All right. Okay, so let's see a bunch of results. These are very preliminary results. I think a lot of the weight is on the many open questions that we have. So especially for people that are looking for an interesting model to think about and maybe to make the first contribution in this field. But we hope you'll find the things that you're looking for. But let's start with perhaps the weakest fully adaptive adversary that you can imagine. So this is an adversary that doesn't have randomness, doesn't have persistent memory. It's a memoryless one. So it only has the estimate memory and the working memory. It only sees the last output and must make a decision, must choose an update, only based on this last output. So this adversary seems to be extremely limited. And indeed, perhaps unsurprisingly, you can get efficient deterministic robust streaming algorithms against such adversaries. Yes, so it's logarithmic in the length of the stream and in the universe size, and we have some overhead, which is the size of the output space, the log of the size of the output space, divided by the approximation time. So this is for the deterministic memoryless adversaries that don't have any persistent memory. And in general, in all of our results, so our results will generalize to adversaries that have bits of persistent memories with an overhead of 2 to the big. All right. So let's see proof of this result. It's pretty simple.
This is actually like any function.
Anyhow,
So can I just go back to the model? So is this adversary actually weaker than an offline adversary?
not just this adversary, but in fact, none of the results we will see assume that the adversary knows the time. It's so weak that it doesn't even know the time. I mean, to know the time in this model, you will need at least a logarithmic number of persistent bits. Without them, not. So this is one of the precautions. Yes, I mean the results are about absurdly weak adversaries, and yet even there it's not completely trivial how to do that. Okay, so let's prove the deterministic result. So basically, if an adversary is deterministic and it sees a certain output, it will always produce the same input, the same output. And now, if the number of outputs that the algorithm produces is pretty small, then the number of inputs is also going to be pretty small because it's just proportional to the number of possible outputs. So if the output space is of size alpha, you only need to do sort of a multiplicative like epsilon net. You only need to like look at all of the values, like all the 1 plus epsilon powers up to alpha, and not too many of them. And these are the only outputs, the only algorithm outputs that are needed. So the algorithm just maintains the number of non-zero entries in the frequency vector, and it only and it rounds to the closest power. And because the number of powers is small, there's not much the adversary will see. So there's only a small number of possible entries, possible updates that it can generate. So we have sparsity, and because of the sparsity, the space consumption of the algorithm is pretty small. Okay, this is for a memoryless adversary. If the adversary has a persistent memory of size b, then it may have an additional 2 to the b states, and then the number of possible states that it will be in is what you see here in the possible number of outputs times the possible number of internal states. And that's it. That's a deterministic proof. Deterministic adversaries are arguably not very interesting. I think we can hopefully agree. It's not. This is not a very exciting result, but it needs to be said. I mean, it's easy to deal with deterministic adversaries even if they are fully identical. At least for problems where the output is like a real number or some it's like a single number and that you can approximate when an approximation exists.
We have lower bounds or just deterministic?
Lower bounds?
Yeah.
I don't think this is tied for it should be proved for interesting classes of functions f. You can get perhaps a better amount. This is also one of the open questions. I promise that maybe. All right, but what about randomized adversaries? This is obviously the next step. And think of I shouldn't spoil the answer. So if we have an adversary that doesn't have the persistent memory, let's say we think about memoryless now. So it doesn't have the persistent memory, it does have the estimate memory, and it does have the tape of randomness. So it does have two interesting sources, input sources, to make decisions. But still, it's very weak. It doesn't have any persistent memory. It only depends on the last output. And it turns out that randomized memoryless adversaries are already quite interesting. So it turns out that they can generate streams that have a high flip number and high density. And in this way, so if, I mean, this is kind of not a very formal result, but for frameworks that use either where the space complexity depends either on the sparsity and either on the density of the frequency vector or on the fit number or any combination, these kind of basic construction fools these black box frameworks. The construction that I'm going to make is extremely simple to deal with if you build an algorithm specifically tailored to this construction, but it does somehow fool the black box frameworks. It kind of doesn't fool the Woodruff and Joe framework. I mean, I don't want to make it very formal, but in the dense regime, it has a heavy hitter, and the framework deals well with these kind of situations, and so I don't want to make this specific claim. Okay, but this is the result that we have. There is a randomized memoryless adversary, so no persistent memory, that against any correct algorithm, not even a bounded space algorithm, can generate a stream with polynomial density and a polynomial flip number. For flip number, it's a very important parameter in the robust streaming literature. It's the number of times that the value of the function f that we want to approximate changes significantly by a power of complex epsilon during the stream. So either multiplies or divides by a power of complex epsilon. And as I mentioned, so the existing black box frameworks, for the most part, have space complexity that is that depends polynomially either in the flip number or the density. So black box frameworks will require this polynomial in M normal space on this instance. At least if we don't tailor them to a specific construction. And I should say that it is very easy to produce strings that are either high density and small flip number or high flip number and small density. So if you want high density and small flip number, just take an insertion only string. It is easy to create it with a memoryless adversary. Assuming randomness, you just send random elements from the universe, you just only insert them. It's also easy to produce a high flip number with low density, even with deterministic adversary. So the deterministic construction is the famous one that creates a linear flip number. Is that when you see that the output is 0, you insert the element 1, and when you see that the output is 1, you delete it. And that's it. And when you see that the output is like non-zero, you just delete it. Okay, but it turns out that with randomized memoryless adversary, you can achieve both. You can achieve both simultaneously, both high density and high flip number, and cause some difficulties or some specific difficulties. Okay, let me tell you about the strategy of the adversary in this case. So it takes some threshold, which is polynomial in M, and then if the output is lower than the threshold, then the adversary picks a random element. This is where it uses randomness, and it uses one. It uses randomness, and it inserts this random element to the string. And then there are several other regimes. So once you cross this threshold by a little bit between this threshold and 1 plus epsilon the threshold, you still insert. And I mean, once the output of the algorithm, we don't know the intrinsic F2 value, but the adversary knows the previous output of the algorithm. So if the output of the algorithm is in this regime, we insert specifically the element 1. So the only heavy hitter we will have is the element 1 in this case. And then there is another slightly higher threshold, still a little bit above this threshold. And where above it, you only delete the element 1. And in between, you insert or delete randomly for bit 1/2. So you look at a kind of like a representative run of the actual F2 value along this kind of string. So in the beginning, you always go up and cross this lower threshold. And then occasionally, because you do a random walk, because you either insert or delete it for bit 1/2, basically it's going to be the case that you will have sufficiently many flips. By the way, it is not mentioned in the slides, but if you have just one bit of persistent memory, we actually can reach a density of n to the 0.4 and a flip number of n to the 0.8, which basically the existing framework will give an n to the 0.4 space for this construction. Just one bit. By the way, open question, can you do it without this function? So we can get to poly m, but not to this polynomial. All right, now finally the main result is achieved. Still far from what we want, but it's the first step. So given any order invariant of the disturbing algorithm, also known in the literature as SFS independent automaton, so basically any disturbing algorithm whose that only depends, basically makes decisions only based on the current frequency. Okay, so it's maybe I won't go into the definition exactly, but just mention this is the definition that captures linear sketching, which is the most important turnstile streaming algorithm. And so any streaming algorithm that behaves like linear sketching in this way, we can, and in the oblivious world, we don't have any adversary, we can generate from it a robust algorithm with the same space times some small factors, so log n, log alpha, 1 over epsilon, and we have this 2 to the b. And this times the space overhead. So basically the space overhead that we have for memoryless algorithms is pretty negligible, especially if you think of like, if you want to avoid polynomial and space dependencies. Still this 2 to b is not ideal, but again, at least against memoryless algorithms, we do quite well. And the proof idea is to, I need maybe 5 minutes. So the proof idea is to reduce to another type of adversary called the stream merging adversary. And for Samson's tutorial said that the computation passes framework gains popularity recently. So we're also going to use this framework. Yeah, so I'll show the result, but just to quickly mention some applications. So you can do norm estimation efficiently against low memory adversaries. If it's a memoryless adversary that's logarithmic in the length of the string, which is kind of the holy grail in the worst case. Interestingly, there are also streaming algorithms in other domains, for example, in graph streaming, that make use of a reduction to norm estimation. And for example, we get an application for triangle estimation. With this polynomial and everything, it's exponential in the persistent memory size. Okay, but now let's skip to the yet another model of adversary and let's see this reduction. So a stream merging adversary basically generates in the beginning a number, hopefully not too large number, of oblivious strings. It generates them in the beginning. And at any round, it picks one of the strings, takes the next update from the string, and sends it to the adversary. So it can switch arbitrarily between a number tau of oblivious strings. All right, so this is the model. Again, this is the usual adversarial model otherwise. The interaction is as usual. But the adversary can only take inputs from one of the bunch of oblivious strings. All right. Now, in this string merging, for this string merging adversary, how many possible different strings can the algorithm see? So it turns out that it always sees prefixes. It sees the prefix of the first, let's say, S1 updates from string number 1, the first S2 updates from string number 2, and so on. And basically, the input can be characterized as a vector S1, S2, and so on. So the number of possible input combinations, the number of possible input streams that we can see because of the ordered variance is just polynomial in n, is n to the tau. And well, if tau is small, then we get an efficient, robust algorithm. So we basically pay an overhead of tau times the log n, and times the space complexity, the space consumption of the original algorithm. Okay, so this is note that the adversary is not computationally constrained. It can make can switch between the oblivious streams as much as they want to. All right, so this is a string merging adversary, and there is a robust algorithm for this setting. And then the next part of the proof is to show that low memory adversaries are string mergers. And the idea basically is that once for any fixed value of the output of the estimate y, and for any fixed value of the persistent memory, what the adversary sends is basically a fixed oblivious string, or that's samples from some distribution. Just samples from the same oblivious distribution. So how many basically oblivious streams do we need to handle here? So it's basically a number of different states. So it's 2 to the b, the states based on persistent memory, times the number of possible estimates y, which is, as before, pretty small. The algorithms rounds the outputs. Okay, so this is basically the overview. This is what we get in the theorem statement, and this is the entire proof. So we're done with proofs, but we saw 3 proofs in this talk. All of them are very simple. And this is time for to conclude. So before I conclude the questions, I need to conclude with some remarks. So the first remark, as mentioned, is that the adversaries do not know the time, and the memoryless adversary doesn't know the time. And understanding what memoryless adversaries that do know the exact time can do is a very interesting question. Again, our current results give space bound, it is exponential in the persistent memory, so it will get like a linear bound, at least in M. So our current results cannot handle this exact time setting at all. But having said that, so it is possible to maintain time approximately very efficiently with the Morris counters. So our positive result gives an algorithm that deals with memoryless adversary and that know always the approximate time in using space complexity that is quasi-polylog in the length of the string. So we do also have some positive results with time. Another interesting remark, so there's a beautiful line of work by Manuel Scheffel and also to me that considers the problem of missing item finding, MIF, where the goal of the algorithm is always to output an element that was never sent before by the adversary. This is a playground for all sorts of questions about randomness, power of adaptivity, and very interestingly, one of the adversarial strategies is memoryless. So the adversary either echoes, either just outputs the previous output that it saw from the algorithm, or produces a random element. So this is memoryless. And it turns out that here memoryless adversaries, in the robust setting, and so it turns out that in this setting, memoryless adversaries are exponentially stronger than just oblivious adversaries, which is unlike the case in our setting. And to solve this mystery, we should notice that this is not an approximation problem. It's kind of different kind of creature. So it doesn't interfere with the positive results that we saw in this talk. All right. Now some of the many open questions that we have. We have more. I didn't even write all of the questions, but really this is. I think there's a lot of very interesting questions in this round. So I think the forefront is the question of whether we can improve this exponential dependence. If we can make it polynomial, that would be ideal, but it's unclear at this point how to do that. And then there are a bunch of other questions. So for example, our current proof does a reduction to extreme merging adversaries, which seem too strong. They are stronger than what you would expect from a merits adversary that are not completely constrained. And one question is to get a better dependence in this part of tau. Another question is to deal with problems that are not where the output is not like a real number or an integer, but for example, heavy hitters problems where the range is exponential in size. Yeah, I mentioned this. And some other open questions is so whether, for example, the dense sparse heavy hitters framework of Woodruff and Joe can actually by itself deal with low memory or just memoryless adversaries. And perhaps a related question is whether it is possible for a low memory adversary to create high density and high flip number streams for F0. And there are more questions. Can we do better against deterministic adversaries? Can we improve all the dependencies? So there are countless questions. Some of them may be pretty hard. Many of them are hopefully approachable. So and there are more. So let me start. All
right, I think we have time for one quick question while we get the next speaker set up. Okay, all right, let's go for another round plus.
I also have it here.
That's more.